Okay, this is going to be my demo for Engine 3. Let me start off by explaining how I extract the skin data for models. So within the my model converter, I added functionality in my load mesh function to pack in these vectors of these skin meshes and a skeleton hierarchy I created to map string names. These skinned meshes, they just contain an array of these vertex skins, which just hold the weights and the bones. So the magic happens down here. In the bottom of the load mesh, I check if there's a skin applied in the FBX. If it is, I get all the clusters and I map them to their bones using the skeleton hierarchy. And I extract the weights and the indices. Then I normalize the data, and I'll keep track of the top 4 ones with this insert function in the vertex skin. This just does an insertion sort on the top 4 bones so that I keep track of just the top 4. Then once this happens, if the skin was found, I end up writing the skin. If it's not, I set this skin buffer offset to 0, and this is kind of my flag within the engine to see that there's no skin. Then once this happens, within the model loader, if I find this buffer offset, it's greater than 0, I take the data and I apply this, call this apply skin function. This is going to create 2 new vertex buffers, one for the weights and one for the indices. And then how these run is within these vertex shaders for the skin. Here's the 2 new attributes, and what they do is I'll have these within the GPU skinning one, I'll have this shader buffer, and within the CPU one I would have like a uniform with the bone matrices. Then I look them up, the array with the bone indices from the vertex attributes, and I scale them by the weights. And I just do a matrix summation, and that's going to be my bone matrix. That's how I apply the skinning for the models. Okay, so let me explain how I did the compression here. So in my animation converter, I extended my initialization. I have this initialization function. This is going to parse some user settings. And at the bottom here, I got this option that has, if it reads the key E followed by some floating number, this is going to be the compression error. And eventually, after all my animations are loaded, I run my animation compressor with this function with the error. And how my compression works is essentially I go through every animation clip, and I always insert into my compressed frames the first and last one, so right here. And then for every intermediate keyframe, I figure out which keyframes to drop by comparing differences in the bone vectors that span from a child to parent. So how I do this is for every keyframe, using the animation, I do a recursive function that computes the parent and child positions for in the bone space. I subtract them to get a delta vector, I normalize it, and I store it in this output buffer. And so as keyframes transition from time to time, I can compare these directions and take their dot products to get values for how different they are, extract the angles, and compare it against my error. So eventually, for every keyframe, I compute this value, and at the end of this function here, for every keyframe, I push back these pointers to keep track of them. So then when I really want to do the main logic, I go through all these directions for all the previous keyframes, and I compare it with the current one. And so I take the dot product between the current one and all previous ones for every bone, and depending on how different the angles are, I accumulate it into this error buffer. And if any bone has a error beyond this threshold angle, I add this current keyframe and I drop all the previous ones. And then I restart this this vector buffer that's keeping track of all the previous ones. And then I keep going for all the keyframes, and eventually I'll get a good result for compression, and I can demonstrate that when I show my engine off. So within the engine, the main logic happens in this skinning demo. So my main functionality occurs in this animation controller, and the animation controller is composed of animations and a skeleton. So for these demos, I have this private load functionality. This is going to trigger my animation loader that has a skeleton and animation clips. and this guy's going to load the animation clips and skeleton into this output structure, and the animation controller will create it using a skeleton, either if it was from the file or because I can share skeletons across many instances, I can also pass into this function. And therefore, so that's how I generated a skeleton controller from the animations in the skeleton. And this is a game object, so that's how it's updated. And then so if I want to do GPU skinning, I have this push function to push the data to the GPU. For the controller, I want to generate two buffers. One is going to have these local bone matrices, and the other one is going to have the world bone matrices, which are the concatenations of all the child and parent matrices based off of the link table that you can get from the skeleton that shows like what indices in the hierarchy are linked to this bone. And then the other part, if I want to do GPU skinning, I also have to push the animation data for the animation, and for this guy he has 3 buffers, actually 4. 3 of them are for the rotation, translations, and scales, and one of them is this output buffer that has a transform. So the compute share that does this is it runs in this update animation function. Within this GPU, I'm gonna bind the buffers for the translations and the outputs, as well as find the keyframe. The keyframe I generated in the update function to get the proper keyframe location. And this update animation shader is just gonna take these all the buffers and just gonna linear interpolate them based on the input blend factor and the keyframes. So the animation controller controls which animations are used by the model. So if I'm just doing a single animation without blending, the process just goes from this shader, and then the animation controller takes that animation and it runs through this pass-through compute shader that transforms this transform that I outputted from the animation shader into a matrix. And then this function is passed then to this link compute shader, and this guy's going to take these local matrices and it's going to concatenate them based off the parent table. Yeah, and if I have blending enabled, the process changes because now these animation compute shaders that updated here, there's going to be 2 of them running for each animation. And then this intermediate shader runs that takes these output buffers and it's going to blend between them. And then it goes to the same process to this guy. And this animation controller is accessed by graphics objects, so then they can access the buffers and bind them to the shader that is going to run right here, or in this guy right here. Okay, and let me start to show off how this works. So essentially, this skinning demo is just going to load up all the animations, compressed and not compressed, and it's just going to store all the data and create game objects from them, and then the graphic objects are created right here. A GPU skinned or normal skin takes in the controller, and eventually when these are bound, it's going to get the buffer and it's going to bind to the shader. Okay, so let me run the demo to show off the features. Okay, right, so this is the first Teddy ones. So here's this little information dialog here. It has the name, animation name, so it can differentiate between compressed and not compressed. So if you look at these 2, compression error and keyframe count, it'll give you some detail about how the functionality works. So Teddy, this one has the non-compressed is 42 and 100 angle compression is 11. So now you can see the blending happen between the 2 animations. So not much redoing 20, these are pretty trivial animations, but you went from 140 to 16 with still pretty good results. The humanoid one is much more interesting. So the uncompressed is 87, and at most compression I have 18. And I also implemented a bounding sphere for animation with keyframes, but just so I could do ray casting on them, I could move them around. So you can see I moved the last one around. Right, and so let me go to, so this one at 87 with, this is almost the same. So 18 to 87, and it looks pretty decent. Let me go to the next animation, the kicking one. 35 is uncompressed. 11 looks pretty decent, but probably these ones look better. So I can move them around with the mouse. And then so next one is 55 to 17. These look pretty decent, look pretty much the same. So I can go compression here. All these little buttons here, they can do things like pause the animation, unpause it, turn off looping, so when it stops you have to replay it. You can go in reverse mode or forward. You can enhance the speed. Okay, and then you'll keep going through the animations. So this one was 52 uncompressed, 20 at the highest compression. This guy had 23 at 70. So these look pretty good compressed. The main one 458 and 71. So you get a lot of savings here, and they look basically the same. This jumping one, see the blending is pretty smooth here. 179, and this one is 33. So look fairly similar. Lots of savings. So 226 to 49, 60 at 70, 86, so 135 to 27. Yeah, so lots of good savings from this compression mechanism. Let me quickly show off these other two animation models. This Golem, so this guy's at 61 to 3 at idle, so pretty much the same. Next one, it goes 61 to 6. Kind of see a bit of less movement for 6 keyframes from 19. 25 to 8 looks pretty similar, so lots of good savings here as well in this model. And this wolf one has got one animation from 7 to 17. 22 to 6, pretty good savings. Yeah, so 100 to 60, 1000 to 63, and looks fairly similar. So lots of savings from this compression scheme. And yeah, that's essentially my demo for Engine 3.